Today we will discuss solutions of some problems. The ability to solve problems is very important. It's the main skill the student should acquire during studies at this institute. So, besides this Saturday, we will have a written test from 3 to 6. A written test will include 5 problems that should be solved in 3 hours. And that will be a distant event, so everybody will be at home, at his or her computer. And the rules for conducting the written test will be sent to you on Friday, the day before the written test. And now we will consider some problems, including the problems from your home assignment. And I would like to start with problem 12.0, which is very simple here. It says a tall and thin factory chimney cracked at the base and began to fall. So we have a tall factory chimney, and it somehow cracked here at this point and began to fall. Find its angular velocity, omega, and angular acceleration as a function of the angle alpha between the chimney tube and the vertical. So at some point, at some intermediary point, this chimney will have this position while falling on the ground, and this is the angle alpha. And what is known about this chimney? Probably its length, maybe its mass if you need it, anything. So while the chimney falls down, this point is assumed to be at rest. So the chimney is assumed to have a high friction coefficient against the ground, so that the base of the chimney does not slip aside and does not move in any direction. And this point is considered as a fixed, as if there was an axle about which the chimney is rotating, as if there were an axle. If you don't assume that this point is at rest, if you allow for some friction coefficient here and allow for the chimney to slip, for the base of the chimney to slip along the ground, then the solution will be absolutely different, because the equation for energy conservation will have different form. But now, as this point is fixed, we can consider the motion of falling chimney as the plane motion of a solid body with a fixed axis, about the fixed axis, plane rotation of a solid body about a fixed axis. In this particular case, there are 2 equations governing the motion of the chimney. First, conservation of energy, which says that the loss of potential energy will be equal to the gain in kinetic energy. That is, the kinetic energy here is the moment of inertia of this chimney about the axis of rotation, that is about 0.0 omega squared over 2. And the loss of potential energy involves the height from which the center of the mass of this chimney descends. So this is the height. This is the difference in the height of the center of mass. Original position was here of the center of mass, and then as the chimney falls down, the center of mass goes lower and lower, and so the height h grows in time, and so the potential energy loss is larger and larger, and therefore the omega, the angular velocity of this solid body about axis O will increase. And the second law of physics, which is important here and which must be used, is the law of momenta. That is, for a plane motion of solid body, we must take its moment of inertia about the axis of rotation, again about this point, times time derivative of angular velocity, and that should be equal to the torque of external forces acting on this rotating body. So the two laws of physics can be applied to this particular situation, and we hope to obtain the solution, to obtain the result based on these equations, on these laws of physics. So in order to solve these equations, we must specify different quantities which are found in these equations. For example, quantity h. Original position of quantity h of the height was the length of the chimney over 2, that is the half of the length, and then final position will be defined as the same length L over 2 inclined at alpha, so that from the original position I must deduce the final position of the center of mass, final altitude of this point. So that will be L over 2, that is the original height of the center of mass, minus L over 2 cosine alpha, because this leg of the right triangle will be expressed as a cosine of this angle if you know the hypotenuse L over 2, this section, then the vertical leg in this right triangle will be expressed through cosine of this alpha, of this angle. So that's obviously is L over 2, 1 minus cosine alpha. Also, we need to find the moment of inertia of this factory chimney, which can be, which we assume to be a uniform rod of a given mass and given length, so that the moment of inertia about the axis of rotation, which goes through the lowest point of this chimney, the moment of inertia will be that of the rotating rod, which is m L squared over 3. We obtained this formula a few weeks ago. Substituting these quantities into the first equation, we will obtain AMG L over 2, 1 minus cosine alpha equal to moment of inertia, that is 1/3 divided by 2, that will be 1 over 6 ml squared omega squared. And from this equation, it's immediately obvious that we can obtain omega as a function of angle alpha. From this equation, we obtain omega as a function of angle alpha. The mass will cancel. Mass cancels here from this equation. And what remains? 6 will go here, divided by 2, that will be 1 over 3. 1L will cancel. And for the omega we will obtain the square root, because this is omega squared, we will obtain square root of 3 g divided by L 1 minus cosine alpha. That's the dependence of omega versus angle alpha. For each angle, this formula gives the angular velocity of the falling chimney. So this result is obtained from the law of conservation of energy. And the law of conservation of energy for rotating solid bodies applies when no external forces produce work. That is, when the object may be considered as closed. Certainly we take into account the work produced by the gravity force. It's included here, so that the loss of potential energy equals the gain in kinetic energy. But also there is some force applied at this point, at the axis of rotation, because there is some friction, as we assumed in the very beginning. So some force is applied here, but this force does not produce any work, because this point is fixed, it does not move. So the work of this force of friction is 0, and the only work produced is the work of gravity forces, which we interpret as the potential energy, so that the sum of potential energy and kinetic energy is constant. What the second equation can give us? This is omega dot. This is a time derivative of angular velocity. By definition, this is angular acceleration, which we have to find in this problem. So immediately we obtain from this equation that the angular acceleration is the torque of forces acting on this rod with respect to the axis of rotation O. So we can say that this is the torque of forces about the axis of rotation. It's important because if we consider different points or different axes, then the torque will be different. If we consider different, then the calculation of torque will be different. The total torque will not, the total torque will differ, and the moment of inertia will be different. So if we go to some other point of rotation, some other axis of rotation, the calculation of torque will change. It will be different. And the calculation of the moment of inertia will be different. This quantity will change. But the angular acceleration will not change. So in order to obtain the answer to this problem, in order to find the angular acceleration, it doesn't matter which axis of rotation you choose. You may choose any axis of rotation which is convenient for you. So we choose this axis which is convenient because when we choose this axis, we don't have to take into account forces of friction, which we do not know. We don't know forces of friction here. So we choose this axis of rotation in order to eliminate the torque of the forces of friction acting on this rod. And we will have to take into account only the force of gravity. And we divide it by the moment of inertia about the same axis O. So in order to calculate the torque, we have to recall what is the torque by definition. The torque is the force and the arm of the force. The arm of the force here will be equal to L over 2 sine alpha. That is the arm of the force. That is this section. L over 2 is the hypotenuse, and this right triangle sine alpha will give us, multiplied by sine alpha will give us the opposite leg in this right triangle, so that this will be the arm of the force, and the force is mg. The force times the arm of the force will give you the torque with respect to this axis. I remind you, what is the arm of the force? This is the smallest distance between the axis of rotation and the line along which the force is acting. So the smallest distance is this. That is the arm of the force. Divided by the moment of inertia, which we have already mentioned here. So divided by ml squared by 3. 3 will go to the denominator. So in this particular expression, m will cancel. And what we obtain here, L will cancel, one L will cancel. And what remains here? 3 over 2. 3 divided by 2. G divided by L. Acceleration of free fall divided by the length of the chimney. And what else remaining here? G divided by L sine. Sine alpha. That's it. The angular acceleration, which is certainly by definition d omega dt, angular acceleration of the falling chimney as a function of angle. At every angle alpha we can find, we know at this particular moment of time, angular acceleration. Certainly in all these formulas, alpha is a function of time. It's some unknown function of time. You don't know what is this function. And if you try to find this function, if you try to calculate it, you will discover that this function cannot be expressed in elementary functions. It cannot be expressed in trigonometric functions and square roots and something like that. That will be a more complicated function. It's impossible to find this, to express this alpha as a function of time through elementary functions. But it's quite possible to express the angular velocity and the angular acceleration as functions of alpha. Alpha certainly is some function of time which is unknown to us. And therefore, both angular acceleration and angular velocity are functions of time. Omega is a function of time, certainly, and epsilon. Epsilon is a function of time. Any questions? Is everything clear? Okay. Let's go to another problem. Okay. I would like to consider problem 1252 from Irodov, that is from your home assignment. A uniform sphere of mass m and radius r rolls without slipping down an inclined plane set at an angle alpha to the horizontal. So we have an inclined plane set at an angle alpha, and here is a uniform sphere, or a ball, a uniform sphere. And no, it's not quite a ball. A ball is an empty sphere, hollow. But this is a uniform sphere with uniformly distributed mass. And we know the mass, we know the radius of the sphere. And we have to find the magnitude of the friction coefficient at which slipping is absent. So the statement of the problem specifies the condition that the sphere rolls down without slipping. And we have to find at what friction coefficient is this possible. It's obvious that in case the friction coefficient is 0 or close to 0, then the sphere would slip down without rolling, practically without rolling. It will slip down like from an ice hill, ice slope, as if it were icy slope. Then the sphere would just slip down without rolling, practically without rolling. So in order for the sphere to roll without slipping, we must have some friction coefficient, and we have to find such friction coefficients which will ensure absence of slipping, so that the sphere rolls down without slipping. Okay. To solve this problem, we must consider forces, because the problem deals with the force of friction. So the force of friction is obviously applied to the ball in this direction. That is the force of friction. The same force, equal in magnitude and opposite in direction, is applied to the inclined plane, to the surface, but we are not interested in it because we don't need it. Another part of the force of friction, which is acting from this rolling sphere on the surface, on the inclined surface. We are not interested in this part of friction. We are interested only in that force of friction which is applied to the sphere, because it's moving and its motion is interesting in this particular problem. Another force acting on the sphere is the force of gravity. I remind you that in order to find all the forces acting on an object, you have to find all the interactions of this object with the external world, with all the external objects. So this sphere is interacting, first of all, with the Earth, and that gives you the gravity force of interaction towards the center of our planet. And there is another body with which the sphere interacts, that is the inclined surface. And the force of interaction between the sphere and the inclined surface has some magnitude and direction unknown to us. We don't know from the very beginning, from the very first steps of reasoning, of consideration of this problem, we don't know the direction of the force of interaction between the sphere and the surface, and we don't know the magnitude of this force. But whatever the direction of this force is, we can always decompose the force of interaction between the sphere and the surface into two directions, into two perpendicular directions. One direction is perpendicular to the surface and another direction is parallel to the surface. So the force of the component of the interaction force which is perpendicular to the surface, we denote it by n, vector n, and the component which is parallel to the surface is denoted by F. This is a force of friction. The sum of these two vectors will give you a total force of interaction between the sphere and the inclined surface, but we don't know it. We can certainly find it in the course of solution by solving this problem. We can find it in the end of solution. But we begin our consideration from decomposing this force of interaction into two perpendicular directions. One is parallel to the surface and another is perpendicular to the surface. And we know there is a connection between these two components. The connection is this: the force of friction is less or equal to the coefficient of friction and the force of normal reaction of the surface. So between these two components there is such a connection. Why? Why is it so? Because of definition of the coefficient of friction. This is just the definition of coefficient. We define this quantity, coefficient of friction, as the coefficient in this inequality, so that the force of friction cannot exceed this value. It can be smaller, but it cannot exceed this value. The force of friction is smaller if the body does not move at all, if it's at rest. If the body is at rest, there is no, on horizontal surface, there is no force of friction. It's zero. But the maximum possible force of friction is defined by this quantity, which includes the coefficient of friction by definition. So now when we have indicated all the forces involved in this process, we can use laws of physics, appropriate laws of physics, which can be applied to this situation. Which laws of physics do we know for this particular situation? We know, for example, the law of motion of the center of mass of a solid body. The law of motion of the center of mass says that the total force, the sum of all forces acting on the body, equals the mass of the body times acceleration of the center of mass, acceleration of this point, which I will indicate as the center of mass by C, by letter C. Also, something important is known here. It's known that the acceleration of the center of mass is certainly directed along the surface. It's parallel to the surface. It cannot be directed at any other angle. It must be parallel to the surface, because the ball is unable to jump from the surface and fly into the air. And the ball is also unable to break the surface and fall down through it. It's assumed in such problems that the inclined surface is solid enough not to break under the weight of this ball. So the ball necessarily, this sphere necessarily moves along the surface, and the acceleration of its center of mass is directed along the surface. Absolutely so. It means that all the forces acting in perpendicular direction must give you zero. It means that N should be equal to corresponding component of mg. So if this angle is alpha, then this angle is also alpha. And the component of mg perpendicular to the surface is mg cosine alpha. So we know that mg cosine alpha must be equal to n in magnitude. In magnitude. In direction, these are oppositely directed vectors. And I should have written it like vector an plus m vector g cosine alpha equals 0. The total force acting in this direction perpendicular to the surface must be 0. But when I go from vector notation to a scalar notation to the magnitudes, when I go to magnitudes of these vectors, I know that these two vectors, this component, this is incorrect. This is incorrect. This is not the vector directed downwards. This is the component of the vector along this axis, along y-axis, and this is x. So the component of the acceleration along the y-axis equals, in magnitude, it equals g cosine alpha. So it equals minus g cosine alpha, because the positive direction of y-axis is chosen to be upward. Then this component will be minus. If I choose another direction of y-axis, then this component will be positive and n will be negative. And this equation will not change. Certainly, that will be correct. So we know something about the forces involved here. We know something beforehand. Before solving the problem, we know a lot about forces, because we are sure that the acceleration of the center of mass is directed along the surface, It can have no other direction. That's for sure from the beginning, before we solve the problem. We know that beforehand. So as far as this equation of the motion of the center of mass is concerned, we can say that this equation projected on the y-axis will give you what? The total force acting along the y-axis is 0, and total acceleration along the y-axis is 0. That's it. Along one axis, 0 equals 0, nothing more. But that gives us important relationship for the force of reaction of the surface, and that will help us find the force of friction finally. Force of friction will be less or equal to coefficient of friction times n, and n is mg cosine alpha. So 0 equal to 0 is very useful because it gives us the relationship for the force of friction, which will be necessary, which will be used in other places in the solution. Now we consider the projection of this vector equation on the x-axis. What happens along the surface? Along the surface, there are two forces, mg sine alpha, this component mg sine alpha, and in the opposite direction we have force of friction. So that will be the result of projecting on y-axis, and now if we project the vector equation on the x-axis, then we obtain, in positive direction we have one force, mg sine alpha, minus the force acting in negative direction, that is the force of friction, and that must give you, according to the main equation, the mass times acceleration, and the projection of acceleration on the x-axis is just the magnitude of this acceleration of the center of mass. And the force of friction can be used from here, certainly, in this equation. So that the relationship obtained from analyzing the y components of all vectors, this relationship can be used when you analyze the equation for the x components of all vectors. That law of physics defines the motion of the center of mass of a solid body under the action of external forces. But this equation has nothing to do with rotational motion. And in order to describe the rotational motion, we have to use some other law of physics, which you know well. For a plane motion or planar motion of solid body, the equation is simple. That is the moment of inertia with respect to the center of mass. The center of mass, this point, moment of inertia with respect to the center of mass, times omega dot, which is the time derivative of angular velocity of this ball, of this sphere, should equal the torque of all forces acting on the sphere. The torque should be calculated with respect to the axis of rotation which goes through the center of mass. This force, the force of gravity, is applied to the center of mass, and so that its torque will be equal to 0. So when calculating the torque, we don't take into account this force of gravity because it goes exactly through the axis of rotation. Its torque will be 0 because the arm of this force is 0. So in this equation we have to take into account only the force of friction and its torque, and that will be the radius of the sphere times force of friction. And also it's important to take into account kinematical considerations. That is the, let's put it down correctly, I will indicate this lowest, or the point at which the sphere touches this surface. I will indicate this point by A. That is the point of the sphere which is in touch with the surface at a given moment of time, A. So that the velocity of point C, will be given as the velocity of point A plus radius angular velocity of the sphere. Plus, certainly, I say plus and don't write it. Plus the velocity of point C, the velocity of point of the center of the sphere as calculated from point A with respect to point A. That is r omega, and omega is the same for any point, for any axis. We proved this theorem, that omega angular velocity is a single quantity characterizing the rotational motion of the whole solid body. Omega is the same for any axis of rotation. So radius of the sphere omega is the velocity of the center with respect to point A, and the velocity of point A with respect to the surface is what? It's 0, because this point, the instant velocity of this point is in touch with the surface, and according to the statement of the problem, there is no slipping. If there was slipping, then point A would have some velocity, non-zero velocity with respect to the surface. But according to the statement of the problem, there is no slipping. So if there is no slipping, then this point is in touch with the surface, and its velocity is 0, in touch with the surface, and the velocity is 0 with respect to the surface, the inclined surface. So that the velocity of the center of mass can be calculated just like r omega. And if we differentiate this equation, I will have to put dot here and another dot here, and I will obtain from here that the acceleration of the center of mass, that is the derivative, time derivative of the velocity, bc equals r, and the acceleration of angular acceleration. The angular acceleration is important because it's found in this equation. So that I can take this quantity from this equation and substitute it here. I will obtain moment of inertia with respect to the center of mass times acceleration of the center of mass divided by r. That is omega dot. And that will equal r f, the arm of the force of friction times force of friction, the torque of external force. So I consider two different laws of physics. The first law was the law of motion of the center of mass of the solid body. And the second law is the law of moments, and the law of the external torque, law of accelerated rotation of solid body. You may call it anything. Law of accelerated rotation, law of external torque. Sometimes it's called law of moments, because in some literature sources the external torque is called a moment of force. Sometimes this quantity is called a moment of the force. And this is also a moment of inertia. So there are two moments in this equation, the moment of inertia and moment of external force. So sometimes this equation is called equation of moments. Sometimes, not in every textbook, but in some textbooks you will find such a name for this equation, equation of moments. So we have two different laws of physics. We have applied these laws to a single situation. These two different laws of physics give us two equations, this equation and this equation, after some calculations, some After some deliberations, we obtained two equations. And in these two equations, we have two unknown quantities. That is the force of friction, which is unknown, and acceleration of the center of mass, which is also unknown. Two unknown quantities can be found from two equations, if these equations are correct. If one equation is not a consequence of another equation, then we can find both unknown quantities. Well, in this problem, we have to find the coefficients of friction. So we have to find the force of friction. We don't need acceleration. We have to find the force of friction. If we keep in mind the final purpose of our solution, the final purpose is the coefficient of friction. So what we need is the force of friction. We don't need acceleration of the center of mass. So we have to exclude this quantity from these equations. We have to exclude it. And in order to do so, we may either find acceleration from the first equation and substitute this quantity to the second, or we may find the acceleration from the second equation and substitute the result into the first equation. It doesn't matter which way you go. Both ways of solution are simple. So we can find it, for example, from here. Acceleration of free fall, acceleration of the center of mass will be r squared f divided by moment of inertia of the ball with respect to the center of mass. And this quantity must be substituted in the first equation. And then the first equation will contain only one unknown quantity. That is the force of friction. Let's do it. So we will have mg sine alpha minus f equal m r squared over ICF. And from here we can find f, which will be mg sine alpha divided by 1 plus mr squared divided by the moment of inertia. That's the force of friction. And we know that the force of friction is always less or equal to Kn. So this quantity is less than equal to coefficient of friction times n. And n is the force of normal reaction, which is found here, which is mg cosine alpha. So we obtain some condition, some inequality, which involves all the given data, all the given quantities which are known from this statement of the problem, and the unknown coefficient of friction. So from here, from this equation, we will immediately obtain that the coefficient of friction must be larger or equal to what happens here. mg here and mg here will cancel. Sine divided by cosine will give you tangent alpha divided by 1 plus mr squared over I. And what is the moment of inertia I of a uniform solid ball? We know very well this is 2 over 5 mr squared. We obtained this formula some weeks ago, and it can be substituted here to find the final answer. So that will be tangent alpha divided by 1 plus mr squared divided by mr squared. That will cancel, and if we divide by 2 divided by 5, we will obtain 2 in denominator and 5 will go to numerator. And that will give us what? 7 over 2, or 2 over 7 tangent alpha. So whatever tangent alpha is given to you, this formula will give you the minimum possible value for the coefficient of friction, the minimum at which there will be no slipping. If the coefficient of friction is less than this quantity, then the sphere will slip down. There will be some slipping. It doesn't mean that the sphere will not roll. It will roll because there will be some coefficient of friction, but the sphere will go down rolling and slipping at the same time, slipping along the surface. So if the coefficient of friction is small, smaller than this quantity, then there will be slipping of the sphere on the surface, on the inclined surface. In order to avoid slipping, in order to exclude slipping, you must take such a surface which has coefficient of friction large enough, larger than this quantity, so that there will be no slipping. That's it. That's the solution to this problem. Any questions? Is everything clear? Will you be able to solve a similar problem at the written test? Okay. Now I will consider a somewhat more complicated problem. A little bit more complicated. So, let there be a cylindrical surface. And a sphere. Again, we will have a sphere which rests on the upper point of cylindrical surface. And the radius of this cylinder will be uppercase r, and the radius of this sphere will be lowercase r. And the sphere starts rolling down without the initial velocity. It starts rolling down. The sphere starts rolling down without slipping again, without slipping. So something similar to the previous problem, but now the inclined surface has no definite angle towards the horizontal, but the angle varies with the motion of the sphere. The sphere slides down and it goes along this cylindrical surface. And we have to find the point at which the sphere will somehow lose contact with the cylindrical point, with the cylindrical surface. The sphere will be disconnected from, will somehow be disconnected at some particular point. And we have to find this angle, let it be angle alpha. It's obvious that the sphere will not roll down infinitely, always touching the cylindrical surface. It's obvious that somewhere the sphere will be disconnected and will fly on its own without any connection with the surface. And we need to find this point of disconnection. We need to find the angle alpha between this point and the vertical. Again, we can use the law of conservation of energy here. Law of conservation of energy, which will give you the simple result consisting in the statement that the loss of potential energy of the sphere will go to the increase of its kinetic energy. But in this particular case, the kinetic energy of the sphere will consist of two terms. First will be the kinetic energy of the motion of the center of mass, that is, with the velocity of the center of mass. That will be the mass of the sphere, the center of mass velocity squared over 2. And also the sphere will not only move translationally, but it will rotate, and it will have some rotational kinetic energy, which will be calculated as the moment of inertia of the sphere, calculated with respect to the center of mass, point C, and omega squared over 2. And again, as in the previous problem, h will be calculated as the total initial height, which is capital R plus lowercase r, that is the total distance from point A to point C, minus the final distance. That will give you 1 minus cosine alpha for any angle alpha while the sphere rolls down and is in touch with the surface for any such angle alpha. The loss of potential energy, the height at which the center of mass goes down, will be calculated as in the previous problem. The total distance from the center of the latch, from point A to the center of the sphere, minus this distance, which can be calculated as the same distance from point A to the center of the sphere, cosine alpha, which is the leg of the right triangle. Also, omega here, in the same way as before, is the velocity of the center of mass divided by r, or the radius of the sphere. The radius of the sphere times omega will be the velocity of the center of mass, as in the previous problem, as in the previous solution, the same. So that the first equation will give us the following: mg, h, and h I will take from this expression capital R plus small r, 1 minus cosine alpha, and that should be equal to mvs squared plus moment of inertia is 2 over 5 divided by 2, that is 1 over 5 m small r squared times omega squared, which is velocity of the center of mass, vs squared divided by r squared. R squared will cancel here, and from this equation also the mass will cancel, and here we will find Vc can be factored, and in the round brackets that will be 1 over 2 plus 1 over 5. So in the end we will obtain 7 divided by 10 Vc squared. The common denominator will be 5 times 2, which is 10, and in the denominator we will have 5 plus 2, which is 7. So that from the first equation, from the first law of physics we have used here, from the law of conservation of energy, we may obtain from here the velocity of the center of mass squared, which will be something's lost here, don't you see? H is here, mg, G is here, R is here. Oh, that's okay, that's okay. It seemed to me, for the moment, it seemed to me that the units of measurement are broken, but no, everything is okay. G is meters per second squared times meters, that is exactly the velocity squared. So everything is okay here. And that will be 10 divided by 7 G capital R plus small r 1 minus cosine alpha. That's the result obtained from the law of conservation of energy. Velocity of the center of mass of the sphere as a function of alpha. Now think about the moment when the sphere is disconnected from the cylindrical surface. What happens at this particular moment? Why the sphere rolls along the surface? Because there are some forces which press the sphere against the surface. And so when the center of the sphere goes along the surface, the center of the sphere describes a circular trajectory. And when the center of the sphere describes the circular trajectory, there is always a centripetal acceleration. Centripetal acceleration, A, is always the velocity of this point squared divided by total radius of the trajectory. And the total radius is the radius of the sphere, capital R, plus the radius of the cylindrical surface, capital R, plus radius of the sphere, which is lowercase r. So this is the centripetal acceleration of the sphere. If we multiply this acceleration by the mass of the sphere, we will obtain the total force acting on the sphere in the direction connecting the center of the sphere and point A. Total force acting in this direction. What force acts in this direction? I will draw it separately. So this is the sphere, and this is the force of gravity, mg, and also there is a force of reaction from the surface. Whatever force of reaction from the surface is, we can always decompose this unknown force into two components. One is perpendicular to the surface, which is denoted by N, and another is parallel to the surface, which is denoted by F, force of friction. So if we consider forces acting perpendicularly to the surface, then we must take into account this force N and mg, the component of mg, which will be, if this is alpha, then this is also alpha. The component of mg will be mg cosine alpha. That is the component of the weight mg of the sphere along the line connecting the center of the sphere and point A. So there are two forces acting in this direction along the radius of the trajectory. The center of the sphere moves along some circular trajectory, and the circular trajectory has its own radius, which is equal to capital R plus small r. This total radius of the circular trajectory gives us the direction perpendicular to the surface, and along this direction there are two forces acting. That is, the first force mg sine alpha, and the second force, which is acting in opposite direction, is N, the force of interaction of sphere with the surface and directed the component of this force of interaction, which is directed along the line perpendicular to the surface. So this is the this is what law of physics is this? We have discussed this law during the previous solution of previous problem. Total force acting on the sphere in certain direction equals the mass of the sphere and the acceleration of its center of mass. Acceleration here is the centripetal acceleration, directed to the center A. So what is this? This is the law of motion of the center of mass of a solid body. We discussed it during the previous solution. That's why I'm introducing it so quickly. You should understand that the total component of the force at any direction will be equal to mass times component of acceleration along this direction. This is not the total acceleration, this is just the acceleration directed at point A. And this is the total force again directed at point A. This equation gives us a clue what happens when the sphere disconnects from the surface. At this very point when the contact is lost, the force of interaction will be zero, the force of interaction of the sphere with the surface. This perpendicular force will be zero. When the connection is lost, when the sphere does not touch anymore the surface, the force of interaction with the surface will be zero, exactly at that angle which we need to find when the small sphere will disconnect from the cylindrical surface. So what remains here in this equation? The mass will cancel, and we can find velocity of the center of mass squared from this equation. That will be capital R plus small r g sine alpha. Such must be the velocity of the center of mass when the sphere is disconnected from the surface. Here? You think cosine should be here? Yes, exactly so. Thank you. Yes, how could I have made this mistake? This is alpha and this is also alpha, so the component of this force should be alpha cosine, certainly. Thank you very much. And here it's written correctly and here it's incorrect. This is cosine. Absolutely so. This is cosine. So such should be the velocity of the center of mass of the sphere at the angle alpha at such a moment of time when the sphere disconnects from the cylindrical surface. Disconnects. And the previously obtained solution for the velocity. This is the velocity, the same velocity of the same point obtained from the law of conservation of energy. It says nothing about the connection of sphere to the surface or disconnection from the surface. It says nothing about that. It takes into account only the conservation of mechanical energy. And from here we obtain the relationship between the velocity and the angle. And this is another condition for the disconnection. So we may equate this expression to this expression and obtain the condition for angle alpha at which the disconnection will occur. So this must be equal to r plus r in round brackets g cosine alpha. So we take now this condition, this equation, to find cosine alpha. R plus r will cancel, and g will also cancel, and what remains here is very simple. condition. That is 10 divided by 7, 1 minus cosine alpha equal to cosine alpha. From here we obtain 10 minus 7 cosine 10 minus 10 cosine alpha equals 7 cosine alpha. And therefore 17 cosine alpha must be equal to 10, or cosine alpha must be equal to 10 over 17. That's the angle at which the disconnection will occur, the disconnection between the small sphere and the cylindrical surface. This angle is approximately something like 54 degrees. So at 54 degrees, there will be a disconnection. At approximately 54 degrees. I didn't look into more strict calculations. That's approximately 54 degrees. So we have found the angle. We have found the position of the small sphere at which the small sphere will disconnect from the curved surface, cylindrical surface. And the small sphere will somehow jump into the air and fly as a body thrown at an angle to the horizon. Fly freely at a parabolic trajectory. After that, before that, the small sphere moved along the circular trajectory, and then the circular trajectory will go into parabolic trajectory because there will be no connection with this cylindrical surface. There is one subtle thing about this problem which I wanted to mention. Let's look into the equation of motion of the center of mass. Let's look into the equation of forces. I will write it again. It must be in your notebooks. I have written it on the blackboard, but the equation of forces acting perpendicular to the surface is mg cosine minus n, the force of interaction with the surface, equals m the velocity of the center of mass divided by r plus r. That equation was written on the blackboard. I just reproduce it again, and I want to discuss it a little bit. So, if we found the cosine, then we know the velocity of the center of mass, the velocity at this particular point, And the velocity is such at this critical angle, the angle of disconnection. The velocity is such that this term is 0. But what happens just a moment before? That is the sphere on the point of disconnection. Another moment in time, and there will be a small interval between these two surfaces. The sphere will disconnect. What happens a moment before? The force of normal reaction is maximum at this point, when the sphere is at the upper point. In this particular case, in this point, the force of normal reaction, N equals mg. And then, as the sphere rolls down, the force of normal reaction goes down from this maximum value to 0. Here, at this point, the force of normal reaction is 0 at the point of disconnection. That is the force acting on the sphere from the surface. So at some moments of time, somewhere here, the force of normal reaction is non-zero, but it's very close to zero. It tends to zero, because it was maximum here, and then it decreased and decreased and decreased. And here, at this point of disconnection, the force of normal reaction is zero. So at some interval, this force is close to zero. And we discussed in the previous problem that if this force is small, then the force of friction, which is maximum value is Kn, will also be very small. The force of friction will also tend to zero when the sphere rolls here at the last section of its way along the cylindrical surface. So at some small last section, the force of friction will be very small, and it means that the condition for non-slipping will be violated. The sphere will start slipping. Here the sphere rolled without slipping, but at some final section of its way, the force of friction will be inadequate. It will be not enough to sustain a simple rolling of the sphere, and the slipping will begin inevitably, because at this point the force of interaction between the sphere and the surface is zero. So before this point it was small, it was very small, and as it was small, the friction was small, and as friction was small, there must be slipping of the sphere. If we take into account this slipping, then something will change in the solution of our problem. What will change? The law of conservation of energy will have different form. We must take into account the work of force of friction here, because if point A on the surface of the, no, this is not point A, this is other point B, for example. If the point B on the surface of the sphere slips along the surface, along this cylindrical surface, then the force of friction performs work. And we should have taken this work into account. So not everything is so simple in this problem. From the very beginning, we assumed that the sphere rolls down without slipping up to the very end, up to the point of disconnection. But this cannot be so. At some final section of its motion, the friction forces will be so small that they will be unable to sustain the angular acceleration, the required angular acceleration as it was before of the sphere. The forces of friction will be unable to provide the same angular acceleration which is required for the sphere to move without slipping. So there will be slipping. And so the law of conservation of energy will be written in a somewhat different way, in a more complicated way. And so if you want to solve this problem correctly, you must take into account this effect. And you must carry out calculations accordingly to take into account the slipping of the sphere along the surface on the last section of its motion. There is no slipping here, but there will be some slipping here. And in order to take it into account, we must know the coefficient of friction. If it's not given to us, we may only make this comment that there will be some slipping on the last section, and it will introduce, that effect will introduce some change into the solution. The final solution will be somewhat different, a little bit different, not much different, but it must be somewhat very right if we take into account the slipping on the last section of the sphere motion. Is that clear? The physics must be clear to you. And when the physics is clear, you may solve this problem correctly, but only if the coefficient of friction is given in the problem statement. If the problem gives you the coefficient of friction, then this effect must be taken into account. But if the problem does not give you the coefficient of friction, then it's assumed that the coefficient of friction is so large that the slipping will occur only at very, very small final section of the sphere track. Only the very small, so small that it's negligible. So if the problem does not give you the coefficient of friction, if there is no k in this statement of the problem, then you must understand that the coefficient of friction is large enough to provide for non-slipping motion of the sphere almost up until the final point. But somewhere close to the final point, there will be inevitable a very small portion of slipping of the sphere on the cylindrical surface. Okay, so as we have worked without an interval, now we will finish this lecture, and I remind you that this Saturday you will have a written test from 3 p.m. till 6 p.m. and the guidance will be sent to you on Friday. I will give you a detailed guidance of what is possible and what is not possible, what is allowed and what is not allowed during the test, and how the communication will be organized and what arrangements should be taken on your behalf. Okay, everything you will know, you will learn everything on Friday. So till then, goodbye.